Over 41,000 airports are scattered across our planet, housing more than 23,000 airplanes. Every day, everywhere, air traffic controllers keep pilots and passengers safe from not only collisions, but also wake encounters, which can be just as dangerous. A wake is created whenever a vehicle passes through a medium. A common example are the waves created by a boat moving across a body of water. Aircraft wakes are a bit different.
When a vehicle is flying, it generates high pressure underneath and low pressure on top. So the high pressure wants to go to the low pressure, and so behind an aircraft, you have these counter-rotating vortices. There is this invisible wake with this upwash portion on the outboard part of that counter-rotating, and then a downward on the inside. Think of them as horizontal tornadoes.
Wake vortices are invisible and can continue for several minutes before dissipating, so air traffic controllers must keep several miles distance between airplanes. This can result in inefficient flight paths and delays, especially if portions of airspace are shut down due to things like volcanic ash plumes or severe thunderstorms. Engineers at NASA's Armstrong Flight Research Center are testing new technologies and methods to help aircraft identify where wakes are and avoid them, or even ride them.
NASA's been interested in improving the efficiency of flight from its initial inception, some conventional and some unconventional. And this is really one of the unconventional ways. It's really biologically inspired. If you've ever seen a flock of geese, the reason they fly in a V is that the trailing birds are really gaining efficiency from the lead bird by flying in the upwash caused by vortices generated by the wing in flight. Some of the early formation flights were military in the early 1900s. In 2000 and 2001, Armstrong flew F-18s in formation, but really close, like within 150 feet or so of one another, and showed efficiency that way. We've also done it in partnership with the Air Force on large transports, the C-17.
In this experiment, it's one of the first times that this has ever been tried with a civilian airplane. Civilian airplanes are typically not quite as structurally robust as military aircraft. And the military aircraft tend to have their own specialized data links. One of the barriers to transitioning wake surfing technology into the commercial sector is the cost that would be required to equip a lot of different airplanes with a specialized data link. Currently, the air traffic control system uses ground-based radar to track aircraft. And ground-based radar have a fairly slow sweep rate, so you only get a position update from an aircraft about once every 12 seconds. And you can imagine a typical airliner flies quite a large distance in 12 seconds. Automatic dependent surveillance broadcast is an improvement upon that, where the airplane transmits its position and velocity information twice per second, and it can be very accurate if the airplane is equipped with GPS. So what we're interested in looking at is, can we use this new data link, ADS-B, that the FAA has mandated for all airplanes operating in Class A, B, and C airspace by 2020. Can we use that data link for an application such as wake surfing?
We were using the data link ADS-B between the two vehicles, predicting where that wake would be, and then flying near that wake to try to gain efficiency. In doing so, we were really trying to also prove that we could use ADS-B as a way to do coordinated flight between multiple vehicles. If you wanted to, for instance, avoid the wake, you could still fly closer than what is currently allowed by the FAA so that you could have an increase in aircraft density.
What we're doing is looking at taking the next step, and rather than trying to avoid the wake, we're trying to fly in a particular portion of the wake that has an updraft. The wake consists of two parts. The outboard parts, the air is rising, and in the center of the wake, the air is falling. So if you fly in the area where the air is rising, it's like gliders that soar in thermal updrafts. You can extract energy from that. Flying on the outboard part, the upwash, allows a trailing airplane to retrim itself at a lower angle of attack, which reduces its induced drag. The less drag you have, the less engine thrust that you need. The less engine thrust you need, the less fuel you have to burn. And of course, the less fuel you burn, the fewer emissions come out the back of the airplane. So the ultimate objective of flying in the upwash portion of the wake is to reduce the fuel burn and the emissions of the trailing airplane.
Okay, pilot's airplane. Copy that, then let's go ahead and start moving on to card 9 and give 808 the lead.
We would begin first by positioning ourselves about 4,000 feet back, and then to the side of and above where we estimated where the wake would be. And then we would take what's called a tear, which is just a test point. It's vocabulary used from the wind tunnel, where you take data with the wind off in a wind tunnel and compare that to the wind on. We were going to compare flight outside the wake and flight inside the wake. And then we would step in and down to where we estimated where the wake was.
As we get closer to the wake, what we're doing is we're looking at the data from the instrumentation that we have on board to try to determine if we're getting into the wake's area of influence. It's difficult to see that in fuel flow until you get deep into the wake, but what you can start to see, because one area of the trailing airplane is experiencing more upwash than the other wing, it tends to cause the airplane to roll. And so our experimental autopilot was designed to trim that out. And so when we looked at the roll command that our autopilot was having to put in, we could tell that it was starting to sense where the wake was and starting to have to do some work in order to trim its effects out.
PPA is engaged.
TCS release. Saw the engage. Roll command is climbing. We get some long-term oscillations, so I think we're close.
We're going to do a 5-foot step in to crash track at minus 75.
Okay.
Activating command 3, 2, 1, activate.
Getting a little bit of buffeting, very slight. Can you guys feel that I'm back?
Just a little bit, but yeah.
So wake surfing, particularly for commercial aircraft, has a number of barriers to its adoption. One of the prime ones is passenger ride quality.
You can't see it, but the aircraft can feel it.
When you fly in the wake of another airplane, there's the potential that there are some unsteady aerodynamics that cause some vibration in the wing, and that gets transmitted to the passenger's seat, and they'll feel some vibration. So maybe something similar to light turbulence. And so we have special instrumentation on board to measure sound levels within the cabin of the airplane, as well as vibration in the seat rails, so that we can then use some metrics on passenger ride quality to evaluate what would the comfort level be, or the degradation in comfort level be, when you're doing wake surfing. So that's one of the concerns that we're trying to answer. Another is, what are the effects on the aircraft's structure? Typically, airplanes are designed for flying in a continuous airfield, not necessarily flying in the vortex of another airplane for any long period of time. It doesn't do any good to implement a technology that saves fuel if it requires the operator to do more maintenance and to take the airplane out of service more frequently so that they can inspect it and replace parts and things like that. We want to make sure that this technology doesn't wear the airplane out quicker than it would normally.
PPA is engaged.
TCS release.
Okay, pilots, this is TCM. As you can feel, we're right on the wake, so we're going to try and sit here as long as we can. Hopefully we can do about 5 minutes here.
What we're noticing on this flight, I think, is that the power required to maintain a constant position when our wingtip is in the wake is less than it is required when we're not in the wake, which means we're going to save fuel, that's the idea.
For aircraft that are flying 16 to 18 hours a day, it's a lot of fuel, even to save 1 or 2%. And so that's what we were looking at, was ways that you could improve the efficiency of vehicles by not changing the vehicles at all, but by changing how we use them, or operational efficiencies.
Okay, and point complete.
Okay, pilots, this is TC. I'm going to do a 300 step out to minus 400.
I was even surprised by some of the flight dynamics and things that we saw in flight. There really is no substitute for taking an experiment to flight. You learn things that sometimes you don't want to learn, but you also see the beauty of the real atmosphere and the challenges that are associated with real vehicles being flown by real systems and real pilots. So you can do lots of simulation and you can do lots of experiments, but you eventually have to take it to flight. And that was really the focus of this experiment was, even though there were lots of predictions that were well sustained, we wanted to take it all the way to flight to find out the things that we don't know, because you're often surprised by the things you don't know.
So based on the results of these flight tests, we believe that we'll be able to show a significant amount of drag reduction and also make a determination as to whether the ride quality associated with that level of drag reduction degrades the passenger comfort level or not.